Hi, everybody. Welcome to my new hire presentation. This is probably the closest that I'll ever be to being on television, so very excited about it. I'm also excited to have an audience that doesn't interrupt. So all these things are going to be wonderful, and I think we're going to have a great 10 minutes. So please go to the next slide. I know you're thinking, who's this random guy? Well, I actually work at PSI. I'm pretty new. I'm an oceanographer. And some of the things I study are vortex physics, large-scale planetary turbulence, ocean-atmosphere interactions. I also do a lot of work on the methodological side. So I study time series analysis methods, and more recently, data mapping methodologies. And I've entirely worked on oceans here on Earth, but I hear there are other oceans out there, so I'm curious to learn more about those from you guys. I also do some teaching, which I'll tell you about a bit later. Next slide, please. So just to orient us, here's everyone's favorite planet, showing some absolutely beautiful vortex structures that you can see. And these vortex structures, you know, the amazing thing about vortices is that they exist on all different scales and all different planets, all different fluids. So those are some very famous ones. But if you go to the next slide, you'll see that here on Earth, in Earth's ocean, we also have similar vortex structures. On the Earth, since it's more of an ocean than an atmosphere, you have much smaller scales than you would on Jupiter. So relative to the size of our observing systems, the ocean vortex population is actually very small and hard to observe. But it's an important part of the climate system. So I've spent a lot of my career trying to document it and understand it both from an observational point of view and also from a theoretical point of view. Now, on the next slide, this is the instrument that was taking those beautiful pictures of Jupiter, very advanced spacecraft, very impressive. I'm sure a lot of you have worked on it. And on the next slide, and this is how we study the ocean. We literally throw things overboard. So there's a real contrast of technologies. This is some random guy throwing a drifting instrument overboard. And what you see is cardboard there that's going to dissolve. But this instrument's then going to drift around with the water following the currents. And next slide. So this very small instrument is called a surface drifter. It has a balloon that's tethered to a long sock, and the buoy, rather not a balloon, the buoy has a GPS on it and also can communicate with satellites. So what you get from one of these guys is where the water is going. And if you have 1,000 of them, then you have actually a pretty great idea about what the ocean currents are doing at any moment, recording all their structure and all their variability. And this is one of the, I would say, central data sets we have for studying Earth's ocean is this drifter data set that is made by NOAA. Next slide. So this data here, we're looking at it in the Gulf of Mexico, these drifting trajectories. So just to orient you, you've got Florida there on the upper right and the Yucatan in the middle, Cuba on the right-hand side. There's a major current called the loop current, which follows that heavy black curve and then goes out through the Straits of Florida that eventually becomes the Gulf Stream. So each of these colored lines is one trajectory from one instrument. And as you can see, there's a very dense network of these trajectories. The black dots here are the launch points, and the gray line is the continental shelf. So from an observational point of view, the challenge with a data set like this is trying to make sense of information that is not localized at each grid point as you might prefer it, but rather is distributed randomly following the turbulent fluctuations of the fluid. So it's a real beautiful challenge to try to extract information out of this rather than just doing the obvious thing and, for example, taking averages. So myself and colleagues have spent some years, actually more like a decade, refining some non-stationary time series analysis methodologies to extract information from data sets like this one. And on the next slide, you get a picture of what kind of information we can get out. Here we're seeing actually the signatures of those vortex structures, which I showed you earlier, happening at all different scales in the Gulf of Mexico. And the color here is representing the frequency. So the red is kind of a more intense vortex. And this picture it's coming straight out of that one I showed you before, the drifter data, but we're able to extract signals that are otherwise buried in noise. But when you can strip them out, you get a whole bunch of information that no one has ever seen before. So this is showing the vortex structure in the Gulf at scales, I would say, an order of magnitude finer than had been previously seen. So that was recently published, and we'll be working on the Gulf in the future. And also, next slide, I'll be working on a project investigating the vortex population in the whole Earth, using this whole data set over the next 4 years. I recently brought that grant to PSI. So we're going to skip a couple more slides. I was going to tell you a little bit more about what I'm doing with along track data which is from a satellite measuring the sea surface. There's a whole other method that we developed for that, but we'll just skip over it for now because want to get to the end. And we'll skip over that, although it's a really beautiful slide. Just so you know, here's a kind of laundry list of the things I'm interested in, both from on the physics side and also the data analysis side. And moving on to more important things. I thought you should all know what my favorite Greek letter is. Well, it's psi, obviously. It turns out that I've done a lot of work on wavelet analysis theory, and wavelet is typically denoted with the letter psi. So I just feel right at home here. And I have to say, when I noticed the size buried inside the PSI logo, I nearly fell off my chair laughing. I thought, you guys, that's the nerdiest joke, and I love it. Next slide, please. Also wanted to share with you my new motto / aspiration. You know, sometimes we get reviews back that make us wince, but this just came back from a NASA panel, and they said this description of my work, which really meant a lot to me. They said, quantitatively solid, but qualitatively imaginative. And I thought, you know, I feel like I just won a gold medal because that is exactly how I aspire to work. And I was just very, very happy that the panel noticed that. And then that's the other proposal that is recently funded that I'm bringing to PSI, working with the long track data, which we glossed over a few slides ago. All right, next slide. Another thing that I do is I teach data analysis methodologies. Here I am with a group of students from Germany a few years ago. So I teach 1- and 2-week intensives in time series analysis and data analysis. And this has been building in popularity over the past few years. So I'm teaching once or twice a year, mostly in Europe. Anyway, I'd love to talk to folks there about possibilities for teaching more planetary scientists if anyone's interested. Next slide. Last slide I want to show you is here is a bunch of people all with their eyes closed while I'm talking, but it's not because it was boring. It's because myself and a friend had the opportunity to offer a session on meditation for scientists, and it was a huge hit. So that's what we're all doing there together. And I'd also love to talk to folks more about that because I think it's a great thing for everyone, especially scientists. All right, last slide. You can visit my website and tell me about those other oceans and other planets. Looking forward to meeting you all.